Okay, so this is calculus now. These are my practice lectures, so please forgive any mistakes. I foresee me not being present on, what is it, Thursday. I have to be at what they call a SAC. I'm on the SAC committee at Metro, so I'm not going to be there, but hopefully somebody else will. If they're not, then, you're going to have these videos for reference. Anyways, 4.6, what we're doing is putting together all of the stuff that we've been learning from the previous, 5 sections together in order to basically graph anything we want. Okay, so essentially you don't need a calculator to graph these equations or these functions. You can do it the old-fashioned way, so to speak. Okay, so the process I'm going to ask for you to do on a test or a project will be the following. And it may differ from the book a little, so please, pay attention to what I'm saying and don't go rogue on me. First, I want you to identify the domain. Secondly, get the x-intercepts, the y-intercepts, the vertical asymptotes, the horizontal asymptotes, slant asymptotes. Okay, so if there are no horizontal asymptotes, generally speaking, there will be kind of a slant asymptote, which you'll find via long division. Okay. The x-intercept, you let y equal 0. The y-intercept, you let x equal 0. The vertical asymptote, you let the denominator of your expression equal 0. Horizontal asymptotes, you're talking about limits, infinite limits in either direction. And the slant asymptote is end behavior as well, but the way we find it is via long division. Okay. So after you get all that material, you'll go after the first derivative and the critical points, or critical numbers is what the book's calling those. And then get the second derivative with all your potential inflection points. And then I would want to see 3 sign charts. And then you'll do a graph. So the graph ultimately should look something like this. You'll have your XY plane, and then below it you'll have f of x, and this is where you're plotting any undefined points and x-intercepts. Okay, so find points / x-intercepts. So the undefined points will generally come from your vertical asymptotes. So here are the vertical asymptotes. Okay. So you'll label those, then right underneath it you'll have your first derivative, and then right underneath that you're going to put your second derivative. And of course here you're putting in all your critical numbers and any undefined points as well. So technically, if the function is not originally defined, it's not a critical number, but we're going to include those on our number line anyways, because the derivative, the sign of the derivative can change over discontinuities. The second derivative, the same deal. You're setting it equal to 0, and you're finding potential inflection points. You'll also include those places from, I guess, the domain where it's discontinuous. Okay. So at the end, it should look like this, and of course you'll have test values and signs and conclusions for each one of these number lines. And the first number line, you should be familiar with doing a number line from pre-calculus for the function. And basically what you're doing is saying, is the function above the x-axis or is the function below the x-axis? Okay. It's from all this information here that you should get a very good picture of what your graph looks like. If you need to, you can always do an alternate table, t-table of a couple points to get a better picture. But this is the idea, okay? And these problems are long. I'm not going to joke or kid you about it. I still remember doing these problems 20 years ago when I took calculus. So, okay. So anyway, that's the idea that we want to have in mind as we go through these problems. Okay, so let's go through a whole bunch, you know, 2 or 3 of them maybe. Okay, so we have y equals x squared all over x squared plus 3. And first, I want to get the domain. So the domain of a rational function is all real numbers except where the denominator is equal to 0. And if you look at the denominator here, x squared plus 3, you'll have x squared equals -3. In other words, it's never going to equal 0 in the denominator, not in the real numbers. So the domain is going to be -infinity to infinity. Okay, so secondly, we want to get all the x-intercepts, y-intercepts, and all the asymptotes. So first start with the x-intercept and try to label everything so I know you know what you're talking about, not just putting a bunch of random data down on your project or test. So the x-intercept, you let y equal 0, so I have 0 equals x squared all over x squared plus 3. You have a rational equation, so multiply both sides by x squared plus 3. And essentially what you're doing is setting the numerator equal to 0. Okay, so you have x squared equals 0. Square root property says that if you know, x squared equals b, then x is equal to plus or minus square root of b. In this case, x is equal to plus or minus square root of 0, which is just 0. So our x-intercept is at 0, 0. Let's get our y-intercept. And of course, we expect this to also be 0, 0, but let's go through the work. Okay, so for the y-intercept, let x equal 0. We'll have 0 squared is 0 over 0 squared is 0 plus 3. And of course, that's just 0 over 3, which is 0. So as expected, I have a y-intercept of 0, 0. Okay. Let's go after the asymptotes. So the horizontal asymptotes are from the limits. Okay. So you take the limit of this expression, x squared over x squared plus 3, as it goes to positive or negative infinity. And in both cases, you can see the numerator and denominator are the same. So if you were to kind of just zoom in on those two guys there, you would have the limit of x squared over x squared, which is the limit of 1, which ultimately equals 1. And it will be the same for the limit as we go to negative infinity. So our horizontal asymptote will be y equals 1. Okay. Then we want to go after our vertical asymptote. So for the vertical asymptote, you're taking the denominator and set it equal to 0. And we've already figured out from the first step with the domain that this isn't an issue. Okay, it's a non-issue. Basically, there is none. So normally you would set the denominator equal to 0, but we found in the first step that the denominator is never equal to 0. So this implies there's no vertical asymptotes. Okay, so step 2, I think we're good. Step 3 now, we're after derivatives and all of that jazz. So I don't know if I want to do it down here. It's probably going to be a lot of room. So 3, we want the first derivative. So f prime of x equals, and we have a quotient or a rational function. So you want to go low d high minus high d low. So low is x squared plus 3 times the derivative of the high is 2x minus high, which is x squared times the derivative of the low, again, 2x all over the low squared. simplify this material, so I get 2x cubed plus 6x minus 2x cubed. Okay, so it looks like the derivative is going to work out kind of nice for us. All over x squared plus 3 squared. 2x cubed minus 2x cubed is 0, so I get 6x all over x squared plus 3 squared. Okay, I need critical numbers, and the critical numbers will, first off, we have to worry about, the undefined places. There won't be any, places where the derivative is undefined because the denominator will never be 0. We only have to worry about where the numerator will be 0 then. So I take the numerator and set it equal to 0, and you get x is 0 as our critical number. Okay. Okay, so the first derivative is done. Now I need to move on to the second derivative. So I'll do that up here. Step 4, I need f double prime of x. So I'm just taking the derivative of the result from f prime of x. And again, it's a low d high minus high d low. So low times the derivative of the high is 6 minus high. So it's a little more complicated. You got to do a power rule. So you bring down the 2 and you get x squared plus 3 now to the 1 times the derivative of the guts, which is 2x. Okay. So low d high minus high now times the derivative. Oh, crud. Did I screw that up? Low d high minus high. Where's my high? Okay, so I lost the high part. It's 6x all over the low squared. So I have x squared plus 3 squared squared is x squared plus 3 to the 4th. Now I need to clean the thing up. So what do we get? I can factor out an x squared plus 3 out of both terms here. That'll make things a little easier. Okay. So I'll have x squared plus 3 to the 1st times 6. Maybe I should have factored out a constant as well, right? So here I'll have 2 times 2 times 6, so 24, and then x squared all over the x squared plus 3 to the 4th. And then I can cancel one factor from the top and bottom here, and I'll get, after distributing the 6x squared plus 18 minus 24x squared all over x squared plus 3 now to the cube, to the 3rd. Okay, combine like terms, so it looks like I'll have 18 minus 18x squared all over x squared plus 3, this time cubed. I need potential inflection points, also places where the second derivative is undefined are potential inflection points, but so the denominator is not going to be equal to 0 again, so I don't have to worry about the undefined points. It's just going to be where the numerator is equal to 0. So I take the numerator and set it equal to 0. We'll have 18x squared equals 18. X squared equals 1, and then I see some people are still forgetting the square root property. When you have x squared equals 1, the result will be x equals not 1, but rather plus or minus 1. You get 2 answers there. So these are going to be my potential inflection points that I have to worry about when I go to my number lines. Okay, so at this point we need to take all of this information that we've unpacked and put it into a graphical form. So it reminds me a lot of like, well, I mean, just look at it. You have this little formula, this nice little equation, and from this equation, assuming you know how to do derivatives and stuff, you get all of this information, a page load of information from one little formula. That's the beauty of mathematics right there. Okay, so anyways, we're going to take all this information and put it into our graph. Okay. So I need an XY plane here. Here's my x-axis, here's my y-axis. Below it, I'm putting in 3 number lines now. One for the sign of the function, where is it positive, where is it above the x-axis, where is it below the x-axis. I'm going to put a number line for the derivative, where is it increasing, where is it decreasing. I'm going to put another number line for the second derivative, where is it concave up, where is it concave down. Okay, so on f of x, this number line, you're plugging on x-intercepts or any places where you have vertical asymptotes. So we found in step 2 that our x-intercept is actually at 0. And let's go ahead and plot that while we're at it. So there's a point, the graph is going through that point. Okay. Let's go ahead and then find the sign of this function in the xy plane. So we could do some test values. So test value, let me get a different color. So try x is -1, and then over here x is +1, and you're plugging these numbers into the original function to see the sign of the function. Okay. So in this interval, if you plug -1 in there, you'll have -1 squared all over -1 squared plus 3. So it'll be positive over positive. In other words, the graph is above the x-axis in that interval. If you plug 1 into here, because of the squares, you get the same number. So it's actually positive in both half planes. It's above the x-axis. Let's move on to the first derivative. Well, actually, we have the asymptotes, right? So let's go ahead and put the horizontal asymptote in here. There's a horizontal asymptote at 1. Okay. There were no vertical asymptotes, so I don't have to worry about that. The derivative then, let's worry about that. So the first derivative gave us a critical number at 0. Let's go ahead then and look at the some test values. Again, you can pick the same ones. So long as you don't pick 0, you're good. And we're working with the first derivative now, this expression here, when we do our test values. So -1 into this expression, the denominator is always positive because it's squared. So you just have to worry about 6 times -1 is negative. So you're going to be decreasing in this interval. So it's negative and you're decreasing. In this interval, you plug in 1, 6 times +1 is positive. So you're going to be increasing in this interval. And then at 0, of course, you're going to have, because it's going down and then up, down and then up, you're going to have a min, a relative min at 0. Okay, so you can note that here if you wish, relative min. Okay, finally then, we're going to look at the second derivative, and let's get the formula in a place where we can see it. So the second derivative was right here, and our inflection points, we found that to be plus and minus 1. Okay, so we're going to label those -1 and then +1. And we want to relate everything to the original, to the graph above it. So I'm going to plot those points here and here, so they're in line with the second derivative chart. Okay. So what are we doing? We got to plug some test values into our second derivative in order for us to determine the concavity. So you pick some appropriate values. Okay, and we're plopping these values now into the second derivative formula. The denominator is always going to be positive again, because anything you put in and square it and then +3 will be greater than 0, regardless if you cube it. Okay, so the numerator is all we have to really look at. And the numerator can be rewritten in the form 18 times 1 minus x squared. Okay? So all you need to do is plug these numbers into 1 minus x squared and see if that's positive or negative. Okay, so -2, 1 minus -2 squared, well, that's obviously going to be negative, so it's concave down. You plug in 0, you're going to get a positive, so concave up. And we have inflection point right there. Plug in 2, 1 minus 4 is negative, so it's concave down. We also have another inflection point at 1. Okay. And you can see that the second derivative test confirms the fact that this is a relative min, because we have a second derivative positive over a first derivative critical number. Okay, so let's go ahead and put everything together and plot the result. So we know the graph is getting closer and closer to 1 as we go in this direction. So it must be getting like this and then coming down and bouncing off and then going back up, thanks to what we know about the signs of the function. It's not going through the x-axis. There's a min right here, so everywhere else it's going to be above. It's decreasing in this interval and then increasing over here. And then the cavity says it's concave down, so it has this kind of U shape to it. And then it'll do an S at the inflection point and turn the concave up. Okay, and then it starts increasing thanks to the first derivative, and then it'll do another S and go concave down. And that's our shape. Kind of looks like I don't know, it kind of looks like a weirdly rotated normal curve. Okay, so you can see what you're getting into. These problems can be relatively long. And let's just keep on chugging away at 1 or 2 more. And hopefully you'll see some variations here on this theme. And you'll have a foot up on the homework. Okay, so let's move on. We'll look at number 9 next. I'm going to need some more paper, so uno momento while I do that. Okay, let's see. Our next guy is another rational function, y equals x squared minus 6x plus 12 all over x minus 4. Okay, you sort of hope you can simplify these sometimes, but in this case, I don't think it's, it's going to be x minus 4 or x minus plus 3. It's not going to work because the middle guy, so you never get a factor of x minus 4 out of this, is what I'm getting at. So anyways, step 1, get your domain. Okay, so if you're a rational function, the domain will be all real numbers except where the denominator is equal to 0. So take the denominator, set it equal to 0, it's 4. That's also going to be a vertical asymptote. So the domain, we're going from negative infinity to 4, and then union with 4 to infinity. Okay, step 2 then, we're looking for all of our intercepts and asymptote information. So for the x-intercept, you let y equal 0. And again, essentially what this comes down to is setting the numerator equal to 0. So you need not even mess with the x minus 4 on the denominator. You're just taking the numerator, and you've seen me sort of do this. Just take the numerator and set it equal to 0. Hopefully that's, at this point, not some mystery to you. Hopefully that makes sense. Probably going to have to use a quadratic formula on this guy. So I was hoping maybe we could factor it. X equals negative b, so 6 plus or minus the square root of b squared, 36, minus 4 times a times c. Right here we have a problem. It looks like the discriminant is going to be negative, and you can pretty much stop at that point. Just for completion, I'll put the denominator in there. So 2 times a. But the discriminant is negative. Okay, so we are not going to be touching the x-axis. Okay, so this tells us no x-intercepts. Okay. Let's move on to the y-intercepts. So for the y-intercept, you're letting x equals 0. So I have y equals 0 minus 0 plus 12 all over 0 minus 4. So negative 3 for our y-intercept. Let's move on to asymptotes. So the horizontal asymptote is from the limits of this expression. So we have the limit as x squared minus 6x plus 12 all over x minus 4 goes to infinity. And then the limit as x goes to negative infinity of x squared minus 6x plus 12 all over x minus 4. Okay. So up here, if we do sort of our game where we just pick off the high degree elements and then make a new limit, we'll have the limit of x squared over x, which is x. And then as x goes to infinity, that'll go to infinity. Here we'll have the limit of x as x goes to negative infinity, and so that'll go to negative infinity. In other words, we don't have a traditional horizontal asymptote, but it turns out we'll have a slant asymptote instead. So for the slant asymptote, you have to do long division. Okay, so I take x squared minus 6x plus 12 and divide it by x minus 4. So you're thinking x times x, what times what gives me x squared, right? So x times x gives me x squared, and then minus 4x. Then we have to subtract these guys. Negative 6x plus 4x is 2x. Bring down the next term. What times x is 2x, so obviously 2. 2x minus 8, subtract those, and we don't care about the remainder. Okay. The slant asymptote is just going to be this expression right here, this x plus 2. Okay. And that's what we get. So, you know, you can ask yourself why, and think of it in terms of limits. Basically, this, if you wrote out our division as we normally would, we would write plus 20 all over x minus 4. And if you let x go to infinity, this thing would become 0. So you're just kind of left with an approach to the line x plus 2. Okay, so that's how I reason it. You can think of it in your own way. Let's go ahead and notate our slant asymptote y equals x plus 2. Okay, so our slant asymptote is right here. Okay, so what next? Vertical asymptotes. We sort of already have that material from the domain. We noted that the denominator, x minus 4, is equal to 0 when x is 4. So that is our vertical asymptote. Okay, so we got all of that stuff out of the way. Now I want to worry about derivatives. Okay, so this is going to not be fun. Let's take a look. So step 3, I'm looking for f prime of x. And I'm going low d high minus high d low. So low, so x minus 4 times the derivative of the high. And geez, I'm going to run out of room right here. We'll see. 2x minus 6 minus high, x squared minus 6x plus 12 times the derivative of the low, which is 1. Ooh, I smushed that in. You probably can't see it. I'm sorry if you can't. My stupid camera doesn't move around very well. It's on this arm, and the arm is, if you touch the arm, it'll get out of whack real easy. So it has like 3,000 different joints on it. anyways, here's our expression. I'm going to clean it up now. I'm going to FOIL the heck out of this junk right here. So you end up with 2x squared minus 6x minus 8x, so minus 14x, and then plus 24. And then distribute your negative, minus x squared plus 6x minus 12 all over x minus 4 squared. Do some combining of like terms, so hopefully that's in the works. 2x squared minus 1x squared is 1x squared. Negative 14x plus 16x is minus 8x. And then 24 minus 12 plus 12, and then that's all over x minus 4 squared. I think we can factor that numerator a bit. It's not going to have a common factor with the denominator, though. We want our critical numbers now. X minus 4 equaling 0, that won't technically be a critical number because the original function is not defined there, but we include it in our number line when we go to do our graph. Okay, so we're going to just pretend, okay, it's not really a critical number, but we're going to use it anyways. Okay, so x equals 4 is one of our values, and then we're going to take x squared minus 8x plus 12 and hope we can factor it. I think we can factor this one. So set each equal to 0, you get x is 6 and x is 2. So we get our critical numbers there for our number line. Okay, now we want to get the second derivative. And hopefully I got enough room for this. F double prime of x. So I'm taking the derivative low d high minus high d low. Show low. X squared minus 8x plus 12 times the derivative of the low. So power rule 2 times x minus 4. And then minus the high, which is x squared minus 8x. Whoops. Low d high minus high d low. Sorry, I totally butchered that. Let's try again. Okay, so f double prime, low d high. So I have x minus 4 squared times the derivative of the high, which is 2x minus 8 minus high. So x squared minus 8x plus 12 times the derivative of the low. So you get power rule 2 times x minus 4 times the derivative of x minus 4 is 1, so thankfully I don't have anything to do there. All over x minus 4 squared. Okay. In the numerator, I'm going to factor out a factor of x minus 4, so I'll have x minus 4 times x minus 4 times 2x minus 8. Minus, if you factor out this x minus 4, you're going to be left with 2 times x squared minus 8x plus 12, and then all over x minus 4 squared. Okay, so we can cancel out one factor of x minus 4. Then you just start FOILing. So I have 2x squared. This times this, and this times minus 8x, and then minus another 8x is minus 16x, plus 32, minus 2x squared, plus 16x, minus 24, all over x minus 4 to the first. Some nice cancellations going on here, 32 minus 24. So 8 all over x minus 4. Seems like this should have been to the 4th power back here. So x minus 4 squared is x minus 4 to the 4th. And then, yeah, okay, so not as pretty as I hoped. But still a nice form for the second derivative. Okay, so we need potential inflection points. There really aren't any, but again, we want to note where the second derivative is undefined, even when the original function is also undefined. It will help with your graph and your number line. So here, we'll just call it a potential inflection number, is where the denominator, in other words, the second derivative is undefined. So you go x is 4, and now we have all of our information. Okay. And my lamp somehow is, the power cord is pulling it down. Okay, so again, it's an incredible thing. We have this small equation here, or function, and we unpack it, and we get all of this information. We're even going to get a graph from it. It's incredible. Okay, for math. Let's go now and take a look at at all the information put together. And do my XY plane here. And below it, I'm going to put my number lines. So one for f of x, one for f prime of x, one for f double prime of x. Okay, I'm going to go to my original function graph, label any x-intercepts or asymptotes. So we don't have any x-intercepts, but we do have an asymptote at 4. Okay. So let's go 1, 2, 3, 4. Label that on our number line. Okay. 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. Get the sign of the function to either side of this guy. So I'm working with test values, plugging them into this original function. So we have, let's try x is 0 and then x is 5. So when x is 0 in here, you'll get 12 all over -4, which is -3, which is the y-intercept. So in that case, we're below the x-axis. So we can put a big minus sign there. When x is 5, you get 25 minus 30. So that'd be -5 plus 12 is positive, all over a positive. So you're above the x-axis in that interval. Okay. Let's go ahead and plot that y-intercept and put the vertical asymptote on there as well. So we'll do that in pink. 1, 2, 3, 4 is our vertical asymptote. Our y-intercept, I believe I said -3. So 0, 1, 2, 3. Let's go ahead and plot that. We have a slant asymptote at y equals x plus 2. Okay. So here, of course, I'm kind of crazy for us to talk about this, but the slope is 1. It means you go up 1 over 1. The y-intercept is at 0, 2. Okay, so you just plot it the way you would plot a line. I don't know how you were taught to do it, but 0, 2, 1, 2. And then the slope was 1 over 1, so you go up 1 over 1, etc. I see a mistake in my notes. I'm sorry. Right here, when I multiplied and got -6x plus 4x is -2x. So this should be -2. Sorry about that. And then this will be -2, and then this y-intercept will be -2. So not up here, sorry about that. It's down here. And then you got to go up 1 over 1, up 1 over 1. And that's our slant asymptote. I apologize. So it's at y equals x minus 2. So I just made a mistake in the long division there. What else? Okay, I think that's pretty good for a start. That's all from step 1 and step 2. Step 3, we moved on to the derivative. Okay. So now we have 3 critical numbers to plot on our number line. 4, 6, so I want to align that with the original graph. 6, and then 2. Okay. I'll sort of note that here is an undefined place. You don't have to do that just for me. I'm going to do that. And then we want to zip through and test values and all that jazz, figure out where it's increasing and decreasing. So I'll try x is 0, plug that into the first derivative. So 0 minus 0 plus 12. The denominator is always positive, so you only have to look at the numerator. So it'll be positive. In other words, it's increasing here. Let's try x is 3. Okay. So in this case, you plug in 3, you get 9 minus 24 plus 12. So 9 minus 24 is minus 15, plus 12 is minus. So it's negative and it's decreasing. I'll just put an arrow going down because I'm running out of room. For the 4, 5, 6, I'll try 5 as a test value. Look at this, 25 minus 40 is 15. Negative 15 plus 12 is negative. So again, it's decreasing. And then try something like x is 7. So 49 minus 56 is 7. Negative 7 plus 12 is positive this time. So it's increasing on that interval. Okay. Let's look at then the concavity, the second derivative. And where are you? Here. So we just have this one potential inflection point, but it's not an inflection point because the thing is not defined there. At 4, so let's get the concavity and see if it's the same or maybe it changes over the discontinuity. So we'll try, and we're plugging it into the second derivative formula is right here. So I get a different color. Or are you pink? So x is 0, we'll try, and then x is 5. Okay. So plugging in 0, 8 all over negative 4 cubed, so that's a positive or a negative. It's concave down. 8 all over 5 minus 4 is positive, positive, concave up. And we should be good to go now. We've got all of our data unpacked. Now we just want to form a picture. For our reader. Okay. Okay, so let's take a look here. Going back up to the graph. The end behavior is going to approach the asymptote. So as I go in this direction, it should be getting closer to this. It's negative, it's going through this point. If you go in this direction, you can see by the first derivative it's increasing. So is it going like this or is it going like this? Well, the concavity says concave down, so it should be going like this. Okay? And then as we approach this asymptote, it's increasing, but then, it's increasing. Then at 2, it'll start decreasing, and it's always concave down. So the picture in this interval should look a bit like this. Okay. Note there is a relative max somewhere in there. I didn't find. Well, I guess it's at 2, right? So let's note that relative. You have to really smush this in. Max at 2. Oh, sorry about my handwriting and everything. Okay, then there's a nice big asymptote, and in this direction, it's going to be approaching this asymptote. Over here, we're above the x-axis, but it's decreasing and it's concave up, so it should look like a U in this region. At 6, the derivative is going decreasing, then increasing, so there should be a relative min there. So this is a relative min. I'll just put min. So we're trying to write a relative min there. And then over here there's a max. Okay, and incredible, you know, from that one equation, look at all this information that it transmits. Just, I still remember my professors talking about it when I was younger, and I didn't really get it, but now that everything is kind of encoded inside of me, and I can do this process, it's an incredible thing. That one little line, and that's not like English. Well, maybe it's a little like English, but there's not too many sentences or words in English where you could just have this and all of a sudden what's the implication? It's all of this. Maybe English is like that. I don't know. Maybe I need to study English more. I don't know. Anyways, let's look at one more off of that. And this guy is our logistic equation, which you'll if you keep taking math and you take differential equations, this is one of the important equations for modeling biological systems. So we have g of t equals 10 all over 1 plus 4e to the negative t. Okay. So first off, we worry about the domain. And in order to take derivatives here in a couple minutes, I'm going to rewrite this expression as 10 times 1 plus 4e to the negative t to the negative 1. So, and again, this is called the logistic equation. Okay. I showed you this when we were talking a little bit about second derivatives and talking about zombies taking over the world. And what does the second derivative represent? Well, that's when the rate of change of the derivative is at the greatest place. So you can think of it, you have a graph, and then you're looking at where the slope is changing the most on the graph. So the logistic equation looks like an S-shaped curve where it has a limiting population up here. And then the second derivative would be the inflection point. But if you look at the slope at that point, that's where the slope is the greatest. So it kind of maximizes the derivative. Okay, so anyways, hopefully that'll help us get the information when we go to the derivatives. First, we need the domain. Okay. I believe it'll be all real numbers. Again, if you have a rational expression, the only problem you'll have is when the denominator is equal to 0. So we have an exponential equation to solve. So we have 4e to the negative t equals negative 1, and then e to the negative t equals negative 1/4. Exponentials are never negative, so we can throw this out, this equation, and just conclude the domain is all real numbers, which verifies my picture, basically. Okay. Secondly, then, we want to go after all of this x-intercept, y-intercept, etc. So the x-intercept is where our, for the x-intercept, let y equal 0. So where is this thing equal to 0? It just isn't, right? You try to solve this rational exponential equation, multiply both sides by the denominator, you get a false statement. So that implies there's no solutions. Okay, y-intercept, on the other hand, there actually is one. And you can think of that as kind of your starting population if you're thinking about zombies, the starting infection. There's 2 zombies escape from the hospital or something. So the y-intercept, let x equal 0, and we have g of 0, basically. I'll just write y, is 10 all over 1 plus 4e to the 0. okay, which is 10 all over 5, which turns into 2. Okay, so 2 zombies in the beginning. We want horizontal and vertical asymptotes. So the horizontal asymptotes, there's actually 2 of them here, 2 different ones. The limit as x, or rather t here, I know I'm supposed to write t, try to fake it. So the limit as t goes to infinity of 10 all over 1 plus 4 e to the negative t. This e to the negative t, if you just zoom in on that, the limit as t goes to infinity of e to the negative t, that was one of our special limits from our limit chapter. And when you plug in t values 10, 100,000, you get e to the negative 10, which is 1 over e to the 10, e to the negative 100, which is 1 over e to the 100. And what you're getting is 1 over something huge. So this part of the expression is going to go to 0. Okay, so we can say that this part goes to 0, and we're left with 10 over 1. So in the positive direction, the asymptote is going to be at 10. So you can say this line right here is y equals 10. Then let's take a look at the limit in the other direction. And it's a little weird with rational equations. You tend to get the same limit in both directions. But for this, no. So you get 2 different horizontal asymptotes. Okay, so in this direction, if you zoom in on the limit as t goes to infinity of e to the negative t, sorry, as t goes to negative infinity of t e to the negative t, what do you get? Well, you get 0. Sorry, you get infinity, because you're putting e to the negative 10, which is e to the 10, e to the negative 100, which is e to the 100. You're getting a huge number. Okay, so ultimately what you get is some number L over infinity, which is a determinant type, and that'll be 0. Okay, so we actually have 2 horizontal asymptotes here. You have y equals 10, and then y equals 0. Okay, so if you look back at the graph, the y equals 0 is this asymptote right here. You're never going to have below 0 zombies. You're not going to have negative zombies. Okay, so what else? We need to get derivatives. So step 3, let's go after the first derivative. Okay, and that's why I rewrote the expression in this form. You'll have 10 times negative 1 times 1 plus 4e to the negative t, now to the negative 2, and then the chain rule, we have to multiply by the derivative of the guts here. So you get 4e to the negative, the derivative of 1 is 0, and then the derivative of this is 4e to the negative t times then the derivative of negative t. So you get negative 1 there. Let's clean it up so it looks pretty. We have negative times a negative is positive, and then we have 4 times 10. So 4 times 10 all over 1 plus 4e to the negative t squared. Okay, and I wrote it like this just so you could kind of, because in the next step we're going to see that the second derivative has pieces of the first derivative in it. And likewise, the first derivative has sort of bits and pieces of the original function in it. Okay. So if you got ambitious, you can rewrite it as 10 all over 1 plus 4e to the negative t times 4 all over 1 plus 4e to the negative t. Okay. And then you could rewrite this as what? Well, you could rewrite it as 10 all over 1 plus 4e to the negative t. And this is neither here nor there. This is kind of like what you'll do in the future. And then times, seems like I lost some stuff. Yeah, I lost the e to the negative t here from this. Okay, so this is times 4e to the negative t. So you can rewrite this as 10 over 1 plus 4e to the negative t times 4e to the negative t plus 1, and this is kind of tricky, minus 1, right? You can always go plus minus 1 is the same as 4e to the negative t. It's just 4e to the negative t plus 1 minus 1 is plus 0. So these are equivalent. All over 1 plus 4e to the negative t. And then you'll see, hey, this is 10 all over 1 plus 4e to the negative t times, if you butterfly it, I'm really going down a rabbit hole here, 1 minus 1 all over 1 plus 4e to the negative t. Okay. And then this thing here will have 10 all over 1 plus 4e to the negative t times 1 minus, we can rewrite this as 1/10 times 10 all over 1 plus 4e to the negative t. And then what is this? Well, look, as I was saying, there's bits and pieces of the original function in the derivative. I mean, you get that with all exponentials. See here, you could rewrite this as y equals 1 minus 1 all over 10 times y. Sorry, y times that. Okay. This form here is the differential logistic equation. Okay. And we'll see that general form later on in differential equations. This is some constant k y times 1 minus y all over the limiting capacity. So that's the differential form of the logistic equation. Okay, but anyways, for us, let's write it in a usable fashion. So this is kind of what we need, and rewriting it here, I'll have equals, let's say 40 e to the negative t times 1 plus 4 e to the negative t to the negative 2. And then I don't know if we should even maybe leave it as a quotient rule. I don't know. I mean, when I take the derivative, having it in the quotient form might be better. I don't know. Okay. Anyways, there's our first derivative. The second derivative, then we're going to have to do some more work. And critical numbers, of course. So the critical numbers from this guy, the places where the numerator is equal to 0. So where is 40 e to the negative t equal to 0? Well, it's not, right? And then the places where this is equal to 0, 1 plus 4 e to the negative t squared to the negative 2, sorry. Where is that equal to 0? Again, that's not ever going to be equal to 0. Okay? It's actually 1 all over this, and you multiply both sides by the denominator, you'll get a false statement. So what is it saying? It's saying there's no critical numbers. There's no places where it's going from increasing to decreasing. And if you look at my original sketch, that's true. It's always increasing on its domain. Okay? So we don't have any critical numbers. Okay. For the second derivative, though, you see there's an inflection point here. So there is concave up and then concave down. So let's go ahead and take a look at that. This is page 7. Looking now at the second derivative, and it's a bit easier to work with the differential form to find the second derivative. So now that I think about it, I was originally just going to take the derivative of this, but that's just too much work. So what I'm going to do instead is kind of just take the derivative of this guy here. Okay, so I know f double prime of x is equal to y times 1 minus y all over 10. Okay, and then I can rewrite this as y minus y squared all over 10, and then take its derivative. So this is actually the first derivative, and I want to take the derivative of that. Okay, so for the second derivative, f double prime of x, I'm going to have y prime. So it's the derivative of y with respect to x is 1 times y prime. And then minus, we have the constant multiple rule, so leave the constant in front alone. And then times 2y times y prime. Okay? And then I could take this and simplify it by factoring out the y. The y prime. So you get y prime times 1 minus y all over 5. Okay. To find the inflection points, you just take the bits and set them equal to 0. Y prime equaling 0, we already worked with that in the previous step. It's never equal to 0. So no help there. Then you just take 1 minus y over 5 and set it equal to 0. And so we get y over 5 equals 1, so y equals 5. And you'll learn later that this is just the limiting capacity all over 2. Okay? So the limiting capacity, again, is the highest this value can grow. It's the maximum number of zombies you can have after they go nuts. So we said it's at y equals 10, and certainly the halfway mark is 5. Okay, the place where the zombification is maximized is right here at the inflection point. Okay. Okay, so if you need to know where that is, we can set, get the x value. So set y equal to 5. We have 10 all over 1 plus 4e to the negative t. Multiply both sides by 1 plus 4e to the negative t. You get 5 plus 20e to the negative t equals 10. Subtract 5 from both sides. You get 5. E to the negative t equals 1/4. Let's go back up here. We got an exponential equation. Take the logs of both sides. So you get negative t equals ln of 1/4. Multiply both sides by -1. Do a power rule, so bring the negative inside the logarithm. And you get ln of 4 as our inflection point. Okay, so hopefully you didn't get too lost there. I did a huge workaround for the second derivative, because I was not about to take the derivative of this thing. I've done it before, but it's a nightmare, and this is more instructive because this is what you do once you get into differential equations. Okay, so there's that. Now we want to unpack all this information again and put it into a graph. So I kind of have an idea of how this works already. Okay, so I'm going to need about 10 tick marks on the y-axis. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I'll put 11, 12. I know there's a nice asymptote, horizontal asymptote. Let's put that in a different color. At 10. There's also an asymptote at y equals 0. Okay. Let's put our number lines underneath this guy. So I'll have 1 for f of x, or in this case f of t. And I think the book calls it g of t, so let's be consistent. 1 for g prime of t. And of course there's no critical numbers there. But there is an inflection point for the second derivative, g double prime of t. On the original number line, there's no intercepts on the x-axis, so all we have to do is a test value. Let's try x is 0, and plug that into the original function. 10 all over 1 plus 4 times e to the 0 is 10 over 1 plus 4, which is 10 over 5, which is 2. And of course, we found that to be the x-intercept anyways. So let's go ahead and plot that as well. Get this point right here. It's positive, so we're above the x-axis always. Okay. G prime of t, then we'll take a look at that guy. There are no critical numbers, so we just do, again, a generic test value. X is 0. And I'm plugging it into this formula here. If you plug 0 into here, you're just going to get positive over positive. So that's positive on its domain, which is the real numbers, and therefore it's increasing everywhere. Okay. The last value then is the ln of 4 for our second derivative. And as a decimal, I think that's about 1.38. So let's put it out here somewhere. So in here somewhere, we have the ln of 4. And then we want to take values on either side to find the concavity. So we'll try x is 0 over here, and then x is, I don't know, 5 over here. Okay. So I need a formula for the second derivative, and you can figure it out by mixing in the derivative and the original function here. So for 0, I said, if you go back to the original function, it's going to be 2. So we're putting 2 in here. So 1 minus 2/5 is positive. The derivative function is always positive, so we can exclude this in determining the sign, and it's just 1 minus 2/5, which is positive. So in this interval, I'll have a positive, in other words, it's concave up. And then in the other interval, trying x is 5, if you plug 5 into here, you'll have 10 over 1 plus 4 times e to the 5. This will be less than 1. So it's something like 10 divided by 1 point something. So it seems like it's bigger than 1. So you'd get something like 10 point something over, or something less than 10 over 5. So it's going to be 2. So I believe this is going to be negative this time. I'm not going to go through and get my calculator out. It's just if you figured it out, it would be negative concave down. Okay. So finally, let's go ahead and do our graph. So it's approaching 0 in the negative direction. It's concave up. Okay. It's increasing thanks to the first derivative, and it keeps increasing, and then it'll change its concavity. So it'll do an S shape at ln 4, which is about right there, and then it's concave down and approaching 10 in that direction. Okay, so that's your logistic equation. It's another one of these great modeling equations for biology. It's more realistic if you're doing something like zombies, more realistic than the exponential growth model, in that it doesn't grow on and on forever. At some point, all the humans, are going to be eaten up by zombies. So there's not going to be any humans left for the zombies to create new zombies. So the population is limited at maybe, what is this, 10, so maybe 10,000 zombies. We'll think the t values in terms of thousands, or the y value in terms of thousands. Okay, so there's that.